is clear from the bond dissociation energy. You can see it from here. Methyl radical has 439, but you see from the vinyl has 431. Alkyl is 5, 40, 544, extremely unstable, and a phenyl radical 464. So that's the reason these are much unstable than the alkyl radicals. On the other hand, the allyl radical is very easy to dissociate from the precursor, and to make and stabilize the allyl radical, the bond dissociation energy is 364, and in the benzyl radical, it is 372. So here the resonating structures can be drawn. The canonical structures can be, you can easily see that you can draw the resonating structures, right? This radical can now delocalize over this phenyl moiety. Here also this unpaired electron can delocalize over this alkene moiety. So electronic delocalization of the unpaired electron is a thermodynamic way of stabilization of the radicals. So that's the reason that benzyl and allyl radicals are much more stable than the aliphatic radicals, the alkyl radicals, or this type of the vinyl alkyl or phenyl radicals. Now, as I go further to the radical stability, if we have these type of groups over the just conjugated to the radical, you can see this OET group, this CO group, acyl group, a nitrile group, right? These radicals are stabilized much more than the vinyl radical, much more than the allyl radical, or even the benzyl radical. The reason also here is simple, that there is some electron delocalization, as well as we can also describe this type of systems. Acceptor or a donor conjugated to the radical can stabilize these radicals by seeing the molecular orbital picture. A simplistic molecular orbital picture allows us to understand that how groups like nitrile or a ketone or even a donor ethoxy moieties can actually stabilize these radicals. Not only from the bond dissociation energies, also from the so that means the electron withdrawing groups as well as the electron donating groups can be stabilized by conjugation. So this can be easily understood not only from the bond dissociation energy but also from the molecular orbital picture. Let us see the molecular orbital picture. So here you see that, let us see that if I have a electron withdrawing group like a keto group, CH3CO group, or a cyano group, these groups, as I discussed with you, a electron withdrawing group will have its LUMO stabilized, right? So its lowest unoccupied molecular orbital, that's a pi star orbital of those groups like the cyano group or the keto group, will be around here. On the other hand, the radical SOMO is around here. So it combines through a conjugation to form this type of a molecular orbital picture. So that means the new SOMO, when it is conjugated with the electron acceptor group, the new unpaired electron orbital, this SOMO, is now having a much lower orbital energy, and that's the reason that you are being able to stabilize a radical which is conjugated with an electron acceptor group like a cyano group or ketyl group. So you are being able to stabilize this SOMO energy if you can conjugate with a antibonding orbital of a acceptor moiety like a nitro group, a cyano group, or a keto group. Similarly, if we now conjugate with a donor group, if we now conjugate with a donor group, this will be the situation, right? This is the SOMO of the radical. This is the HOMO, that means the non-bonding orbital of the electron donating group. You can consider a methoxy group, a ethoxy group, or a me2 group. So energy of the lone pair is here. the SOMO is here. And now you can see the overall energy of the lone pair, the HOMO of the system has now come down, and that's the reason that you can now stabilize the radical further. Consider this as a now like this. So the overall energy has decreased 2 electrons over here. Although this HOMO energy is higher, but still the molecular overall energy of the molecule is now much more lower and stabilized because of the donating group. It is a little contrary that what we see because the SOMO has actually risen in energy, but then because the HOMO has been stabilized of the overall radical moiety after conjugation with the donor, the system overall has stabilized in presence of a conjugated electron donor with a radical. Now, before I go into the important reactions of the radical formation, I just want that if you please want to ask some questions, please ask. Please feel free to ask me some questions. If you have some questions, please feel.
उधर से पूछ लो ना एक आध भाई एक आध क्वेश्चन पूछ ली
प्लीज पार्टिसिपेंट्स किसी के भी क्वेश्चन है तो आ जाइए
Ma'am, can you just increase your voice a bit?
क्वेश्चन
Voice will not go
Anybody?
there.
बोलो ना
There go, then only we can communicate.
what to say only
Yes, sir.
what to say
They will say.
Or you can maybe write down if you have a computer, if you have a laptop. I'm not being able to.
Sir, I would like to ask one question here. How to control formation of the byproduct in case of longer hydrocarbons? Whenever we are performing free radical reaction, for example, hexane and pentane, more byproducts would form. How to control formation of the byproduct?
So you were asking, I'm not very